Melanie's talk on encoding and verifying Leo3 proofs in the Dedukti framework.
Exactly.
Off you go.
Thank you. Okay, so yeah, the title already gives away which system we're going to verify or try to verify in my talk. It is called Leo3, and like Vampire, this is an automated theorem prover. So maybe after we just saw the last talk and we saw all of the trophies, you may now ask why even bother encoding any other theorem provers. But with Leo3, we're actually based on extensional type theory, so we're working in a high order logic, and we also have a lot of encodings of non-classical logics. So if you have a bit more special interest areas, then you may also be interested in having proofs like being verified. Okay, so Leo3, just like most automated theorem provers, is by default going to output its proof in the TSTP format. And while this is very widely used, as we have already heard, we don't have a guarantee for the proofs actually being correct. And the reason for that is that we can, on the one hand, show that the calculus is sound, but as we have heard before, there are no guarantee that there were no bugs made in the implementation, and therefore we can't guarantee that the proofs in TSTP format are actually correct. So that's the issue that we're trying to tackle in this project, and we're going to do this by also outputting our proofs in the Dedukti framework, and the system that we're translating to is the interactive theorem prover LambdaPy. And we're going to see later in this proof that LambdaPy offers a few features that are really useful and make our life a lot easier. Okay, so before I get into the actual translation, I'm just going to have some background, and I think in this crowd I can go over these slides very fast. But generally, when we have an interactive theorem prover and we give it a reasoning problem, the very first thing that we're going to do is negate our conjecture, and then we're going to try to have a proof by contradiction. So we're going to try and derive a contradiction. The next thing that we're going to do is apply some kind of pre-processing. So usually this is classification. And then we can actually start applying our inference rules. One of the rules that we have in Leo3 is called PFE. That's the one that you can see here. And PFE basically just tells us from the equality of two functions, we can derive that the two functions are still equal on any argument. So this is symbolized by this x, which is just an implicitly quantified variable. So in a concrete proof, we may, for instance, have one step, which is f equals g for two functions. And then from that, we can derive fx equals gx. Yeah, this is one of the inference rules that we, for instance, have in Leo3. And then after the application of these inference rules, we'll check whether we have already derived a contradiction. If this is not the case, we keep going until one of two things happens. We either reach a timeout or we eventually end up actually showing a contradiction. In that case, we can output a proof certificate. So we have some representation of our proof in an abstract manner like this, and we're trying to get to a LambdaPy proof. And for the sake of this talk, we can roughly break this task down into 4 steps. The first thing that we have to do is the definition of a LambdaPy theory. There you go. So that is a representation of our object logic in terms of LambdaPy, of our meta logic. Building on this, we can then encode the individual steps of our proof and the problem, as well as the inference rules. And then based on these encodings, we can try to encode the proof as a whole. So for the first step, which is the encoding of our meta logic, we're going to use LambdaPy. Once again, we've already heard about the LambdaPy calculus module today. So just very briefly, we have higher logic with dependent types and rewriting. The syntax here is just like it was in the last talks, and we have a lot metalogical type of types, which is called capital type here. The object logic that we're trying to encode is, yes, and then of course we're trying to use this meta logic to have an encoding following the propositions as type principle, which will allow us to automatically check the correctness of our proofs by checking the typing of the encoding. So the object logic that we're going to encode here is extensional type theory, which is higher order logic with extensionality, choice, and rank 1 polymorphism. And then when we come to the actual encoding, this very much resembles what we have seen before. Just the naming is a bit different here. So once again, we have set, which is declared as a type. We're going to use set to declare our object level types. In higher order logic, this will usually be omicron and iota. And we also can declare things like our function type constructor in this way. Then we need another constructor to actually encode the objects that we use in our project, just like f here. F is a type from iota to iota, and tau, which we have already encountered in Alessia's talk, just there it was called L, I believe. is going to map our set to a type, and therefore tau iota to iota becomes a type that we can use to declare objects just like f or g. Then also, as we have seen before, we can use the same strategy to encode our object level connectives, just like equality. And since equality should be polymorphic, we use a dependent type here. And then for any arbitrary object level type t, equality is going to take two terms of this type and map them to a truth value. So this is our equality. And then we can use the connectives like this to encode steps in our proof. We yet need another constructor, which is going to take our object level propositions and map them to types. This is going to be what we're using to actually implement the propositions as type principle. Once again, this is something that we have seen before, just in the previous encoding, this was called proof, and that was called pi. So now pi f equals g becomes a type, and we can use this to declare symbols that represent the individual steps in our proof, and we can do the same thing for any axioms that we have in our reasoning problem. So now step m is a symbol that represents a proof of this step in our longer proof. Okay, so this is how we can encode the underlying logic and also the individual steps of our proofs. And then the next thing that we need to think about is the encoding of the actual inference rules. So let us, for instance, consider that we want to now have an encoding of our rule proof E that allows us to go from this step to this step. And the straightforward thing that we can do, and that I'm going to demonstrate here, is the encoding of such a rule as a function. So the idea would be to basically have a function which takes a proof of s equals t and maps to a proof of sx equals tx. And of course, this should hold for any arbitrary functions s and t and for any arguments x. So we can use dependent types for this. So now we can instantiate this with, for instance, f and g. And of course, we also want this to hold for any arbitrary object level types. So we can basically add another layer of dependent typing, which allows us to instantiate our rule with our object level types. And in this concrete case, for instance, in this concrete case, for instance, we can instantiate this rule PFE with iota, iota, f, and g. And then this results in a function that's for any x maps f equals g to fx equals gx. And just as a side note, we've already heard that in actual encodings, we're of course going to define all of our symbols. This is also true for our rules. So when we actually have an encoding of the rules, we're going to provide proofs in terms of our meta logic that actually show that our rules are correct and not just state them like we did here. Okay, so in this fashion, we can encode some of our rules. However, so far, I've actually lied to you when I said that PFE just looks like that, because in reality, of course, we may have longer clauses, which makes our encodings a bit more complex. And this is symbolized in these rules by this or C, which basically tells us that this literal, this equality that we're applying the rule to is just one of the literals that we may have in a longer and more complicated clause. So in our concrete case, this may mean that we don't just have a unit class, which has this one equation literal, but we may have multiple literals and just apply this rule to one of the literals in our class. This, of course, makes our encoding a bit more complicated, because now we can't directly map this step to the next step anymore, since we have to take into account the added structural complexity that we get with the additional literals. And now we need to somehow encode our rules in a way where we can use them on clauses of arbitrary length and for literals at an arbitrary position in our clauses. And the way in which we're doing it in this project, at least, is through the inclusion of an additional theorem. And this we call a meta theorem because it allows us to do these structural operations that are encoded on the meta level. And the idea that we're following here is that basically we would like to have a function that allows us to take as a first argument the rule that actually justifies the modification of an individual literal. As a second argument, it takes the original clause, which includes the literal we're trying to modify. And then what we get is the clause that we're actually trying to prove, where we have modified the literal. So that's the idea, and that's the kind of theorem that we would like to have. And we have proven that as a general theorem, which we call transform. And we need to instantiate this theorem transform with a few things. The first thing is the literal that we're trying to prove. So in our case, this would be fx equals jx. The second thing, and here we're now using some of the encodings from the standard library of lambda pi, is a list of terms of type omicron. So this here is given basically by this L and omicron. So this just declares C to be a list of object level propositions. And this is going to be the representation of our class now. The last thing that we then need is the index of the literal that we're trying to modify. Once again, we're using some standard library encodings here. So this is a natural number, which is given by this typing. And then with this instantiation, we get a function that has directly, or corresponds directly to what we discussed above. So it takes the nth element of our original class and the proof that it implies the literal that we're trying to prove or prime. As a second argument, it takes the disjunction of all of the literals of C. So this basically is just a symbol that rewrites a list of propositionals in the object logic to a disjunction of them. And then what we get from that is the proof of a disjunction of our original class C, where the nth element has been replaced with the literal that we're trying to prove. So this proved very useful for us. And as we expect that some of the other meta theorems that we proved that are similar to that, so some other theorems that operate on complex structures and are very well flexible when it comes to these structures, may also be useful for some other projects. I would just like to briefly mention what other things we've proven here. If any of this looks useful to someone working on similar stuff, I invite you to reuse them. They can all be found on GitHub. So another one of the theorems that we're using, we call select. Basically, this theorem allows us to, if we have a conjunction of an arbitrary amount of literals, derive an an arbitrary amount of clauses. It allows us to derive one of these clauses. This is what we apply after our classification procedure. The next one is called permute. So in this case, if we have a class, so a disjunction of literals, it allows us to prove that we can permute them in an arbitrary fashion. So you can give a permutation as a list of natural numbers, and the theorem is going to prove the permutation of your original class. And the last one is called delete. And this is useful when you have some rules that may delete any double occurrences of literals. So this is something that happens in Leo3, sometimes implicitly. And with this theorem, you can instantiate it with the indices of the classes, of the literals that you would like to delete. And then this provides a proof for the admissibility of this operation. Okay, so back to our concrete proof. Now we have seen how we can encode rules like this, and we've also seen how we can encode the individual steps. And now I would like to show you how we can combine this into proof steps or into proof scripts that actually encode the individual steps in our proofs. So basically here, we once again encounter what we see before. So we have our transform theorem, and we can instantiate it with the literal that we're trying to prove, with the list that represents our class and the index. And then the arguments down here are the instantiated rule and the previous step. So that's exactly what we've seen on the previous slides. And the tactics that we're using here between the keywords begin and end that initiate and end our proof scripts are assume, and assume instantiates our dependent types, so our free variable in this case, and refine basically instantiates the proof term. So in this case, it would be rather straightforward to use an encoding like Dedukti and directly output our proof terms. However, in other cases, the tactics of lambda pi can be very useful when it comes to actually encoding our proofs. And to show you an example for this, I would also like to discuss the simplification rule in Leo3. So the calculus rule simplification looks at all of the literals in our clauses, and then it applies simplification procedures to both the right-hand side and the left-hand side of our literals. And what these simplification procedures do is effectively just exhaustively applying some Boolean identities to, well, simplify our terms. And these Boolean identities are pretty straightforward. So we have things like A and A is identified with A equals A is identified with top, and not top is identified with bottom. So we could, for instance, encounter a term like this somewhere in our proof steps, and through the application of these rules, we would first get A equals A, then this would be identified with top, and then due to the negation on the outer scope, this would be identified with bottom. So this is conceptually quite easy, and we can probably all agree that something like this is obviously correct. But if we want to verify something like that, it can become quite tricky. And the reason for that is that we may find structures like this at an arbitrary nested substructure of our literals. And then the way in which we can construct our proofs is not as straightforward, because even something like our transform theorem is not going to be helpful for us here, because we may be nested much more deeply within our subterms. So for these cases, lambda pi has a very useful tactic, which is called rewrite. And just to be clear, the rewrite tactic doesn't define any new rewrite rules, but the rewrite tactic instead allows us to use proven equalities on a user interface level, almost as if they were rewrite rules. However, it under the hood does construct proof terms that actually justify the operations that we're performing. But as a user, this means if we have identities like this and we do encode them as equalities, so for instance, for the first one, we can just give it a name like and edem, and then it's a proof that every x, and therefore every x and x equals x. Once again, of course, in reality, we will also provide a proof for the correctness of this rule and encode the other rules likewise. And then when we actually construct a proof script for this, what we can do is simply use the tactic rewrite. So here you can see we have a proof script. What we're trying to prove now is that the left-hand side, which corresponds to the original term, is equal to bottom, which is the simplified term. And then the application of the rewrite rule with all of our, the rewrite tactic for all of our identities is going to reduce this term on the left-hand side to bottom as well. So basically, this leaves us with the obligation of proving that bottom equals bottom, and lambda pi can automatically do this if we use the tactic reflexivity. So you can maybe already see that this makes our life a lot easier, because we don't actually manually have to figure out on which substructures we need to apply these rules. And also in the case of Leo3, this is very useful because it directly corresponds to one of the inference rules of Leo3, which is the rewrite inference rule. So when we're trying to verify steps that use the rewrite inference rule, originally we can just do this by using the rewrite tactic in our lambda pi encodings. Okay, so you can already tell that maybe in these cases, the tactics are very useful, and we can take this even further. Alessia already mentioned earlier today that we now have the option to have some user-defined tactics using a term language in lambda pi, and this can be specifically useful for things like simplification. So we can basically, or the idea is to basically encode the procedure that we have in Leo3 that exhaustively applies all of our Boolean identities, and mirror this in a lambda pi tactic using the keywords or else and repeat. And well, they pretty much do what you would expect them to do. So when we want to define this as a tactic, it would look something like this. So you can see here, we first tried reflexivity, and now the things that we've seen before as tactics are prefixed with a hash. So this is just to differentiate the actual tactics and keywords that we need to use as tactics with the term representation of them. And in this case, this tells us that the first thing that we're doing is checking whether the two sides of an equality that we're trying to prove are already equal. And if this is not the case, so or else, we're trying to rewrite with our first Boolean identity, and then we can just go through our whole list of Boolean identities. So this is what the procedure could look like. And to repeat in the beginning basically just tells us to keep doing this until we either can't do anything anymore, or ideally until we have resolved the goal that we're trying to prove. And this then actually makes our proof scripts much shorter, because all that we now have to do is use the keyword eval, which takes one of these tactics that are defined as a term and interprets them as a tactic and carries out the corresponding operations. So in this case, and this is actually what we're doing for the simplification in Leo3, we simply tell lambda pi to evaluate this tactic, and then lambda pi can automatically apply all of our Boolean identities at the relevant positions and resolve these kinds of steps. Okay, This kind of leads us with a general scheme of how we can encode our Leo3 inference rules. The first case that we may encounter is the straightforward one. This is where the lambda pi operations or lambda pi tactics correspond to the rule that we're trying to encode. The simplest case for this is, for instance, the Leo3 rule rewrite, as I already said. And in this case, we don't actually have to encode the rules at all. We can just use the corresponding lambda pi tactics. The second thing that we have already discussed today and that we can encounter is cases in which we encode our inference rules as a function. This is, for instance, useful if we operate on a structure as a whole, or if we operate on a substructure like a literal, but we can't prove inequality between the parent and the child of an inference rule because the child is merely a consequence and not equivalent to the parent. And then we can either directly apply them or apply them using the transform theorem. And then lastly, what we have seen for simplification are cases where we operate on substructures and the parent and the child of our inference rule are actually equivalent. And in these cases, it is proven to be most useful to encode these rules as equalities and then apply them using the rewrite tactic. Okay. There is one more thing that I haven't mentioned so far, because now we have basically discussed the encoding of the steps. We've discussed the encoding of the various rules. So you may think it is now very straightforward to combine that to encode the proofs as a whole. However, and this is something that we've also heard from Anja before, in reality, provers can do some things that you wouldn't necessarily expect from just looking at the theoretical inference rules. At least in the case of Leo3, this is very much the case. So if we revisit the example that we have been discussing today, so far we assumed that given f equals g or l, what Leo3 would derive for us is fx equals gx or l. Well, because this is pretty much exactly what the rule tells us to expect, right? However, in reality, if we would use our prover on this step, what we actually would get is first, Leo3 would swap the size of our equality. Once again, something that we already heard in the previous talk. And for Leo3, this just happens because it applies a term ordering after applying inference rules. And then the second thing that would happen is that Leo3 would reconstruct a new class by just first taking all of the literals that it didn't touch, and then the ones that it did touch. So we actually also would swap the order of the literals in our class. So we have quite some reordering going on there. And this is not the only kind of operation that can happen implicitly. We also, in some cases, have a deletion of double literals or implicit simplification of literals. And of course, all of these things make our life a bit harder because we also have to take these into account when we're doing our verification. The strategy that we can generally follow in the case of Leo3 to encode such things is by just seeing them as additional inference rules themselves. So in the case that we've discussed here, for instance, one of the rules that we would need is permute. And I've already told you that we have encoded this as a meta theorem. And the second thing that we would have to do is apply a inference rule, which basically just tells us that from x equals y, we can derive y equals x for any x and y. And you can see here that this is encoded as an equality because now we can conveniently use it with the rewrite tactic. Okay, so this is the idea. We encode our implicit transformations as additional inference rules. And then on a case-by-case basis, when we are encoding actual proof steps, we consider whether or not we need to actually apply these additional encodings on top of the application of the inference rule itself. And this kind of gives us a modular encoding scheme for each of our inference rules. So for instance, if we return to our examples and we would now want to have a full proof script for the step that we, so for step n it's called here, which is L or gx equals fx based on f equals g or L, then we would basically just consider which of our additional things we need. The first thing that we always do, of course, is the inference rule itself. So this is the first sub-step, which is introduced here with the lambda pi tactic have. We can just give it a name, functional extensionality application. And then the proof is exactly what we have seen in the previous slides. So this is something that's always going to happen when we're verifying these rule applications. But then on top of that, we have to check whether we also have to apply any of the rules that we can apply with the rewrite tactic. For instance, in our case, this is the case. We have swapped the sides of the equality here. So we're going to verify this in an additional sub-step using the encoded rule that we've seen before. So as you see, we just instantiate the rule, then we can use it with the rewrite tactic. And then once again, we know that sometimes when we're applying this rule, we may have a permutation. So in a concrete case, we check whether this is the case. And that has indeed happened here. So we need to swap these two literals in our clause. So the last thing that we do is prove that with the permute meta theorem. So that is generally the idea and generally the procedure that we apply to encode our proof steps. Okay, so this is the general strategy that we're following. And we also have a partial implementation for this. So far, we can handle about 14, or well, exactly 14 of the 26 rules that are relevant for our Leo3 encoding. And when we take this implementation and we run it on a benchmark, I think here as a benchmark, we use the hierologic problems of the TPDP library that we were able to solve within a 60-second time limit. Then we could already encode basically 65% of the steps and the proofs. So this is the metric that we're using here. We just count the amount of steps that we can already verify versus the amount of steps that we had in total in our proofs. So yes, for the future work, of course, the first goal is going to be to bring this number up to 100%. And then building on this, we're going to further extend our implementation. So far, we are only handling monomorphic cases, but as you have seen, or maybe you remember from the first slides, Leo3 actually also handles rank 1 polymorphism. And then some future work would also be to maybe revisit the encodings that we already have and optimize for some more efficient strategies in some cases. Yes. In case anyone also has any questions about references, I have a full slide with things for you to read right here.
Thank you, Melanie. Are there any questions from the audience? Scott?
So how confident are you that you will reach 100%?
Sorry?
How confident are you that you will reach 100%?
I am actually quite confident. So we already have theoretical encodings for the remaining rules and kind of constructed some examples by hand. So there are no like conceptual hurdles. We of course also thought quite a lot about classification, and we're using maximum of choice to encode the columnization steps. And so far, this is already implemented and it's working well for us. So I think for the remaining rules, it will be quite some work to actually implement them. And usually the hardest part or the most time-consuming part is figuring out which implicit transformations happen in addition to the actual inference rule. But yeah, we're quite confident with the 100% are definitely reachable, yes.
I mean, these are the rules for Leo 3. How different are the rules in, let's say, Leo 2 or something? Satellux. I mean, how general is this basically?
So I actually don't know
if there is a Leo 4 that is coming out, I don't know. Will there be 400 new rules or something? I don't.
So I guess it depends. If you have similar rules, so for instance, paramodulation, I expect that you could use the same strategies that we're using for other paramodulation-based systems as well. We also, in these cases, would have to track some more information. So this is, again, something that we have heard from the previous talk, that we need some information about which of the literals we, for instance, use for rewriting and stuff like this. But given this information, I'm sure that the theories that we're using here and the encodings of rules that we're using here would also be applicable for other systems. Just actually getting it to run and then maybe again seeing which implicit other transformations happen in other systems would definitely be a bit of work. But yeah, the theory itself should definitely be applicable to other systems as well.
So I have a related question to one of my questions. So there is no rules in Leo 3 that is related to higher order logic, because it looks like all the rules are just first order logic.
Yeah, we
Functional extensionality is higher order logic.
I actually have the full calculus right here.
It had some type annotations, right?
Oh, perfect.
So there you go. You can also see which of the rules we are already handling. So those are the ones that have this fancy frame. And some are crossed out because they just do stuff like deleting clauses from the search space, so we're never going to encounter them in our proof certificates and don't need to count them. But yeah, we have stuff like paramodulation in our primary inference rules. Yeah, there you go.
So it seems that Leo 3 has lots of these idiosyncrasies, similar to Vampire, where it does all of this swapping and it treats certain things as equal modulo commutativity and stuff. And then these changes don't show up in the proofs. And then you have to keep track of these and know where these things have changed and blah, blah. So that's one approach for dealing with that pain. But another approach is possibly lobbying the people who develop Leo 3 so that in Leo 4 or just a future version of Leo 3, they stay closer to what their rules actually say and make interoperability a bit easier. And I do believe you have some connections with the development team of Leo 3. So have you considered this, even though it's more of a social challenge than a mathematical challenge, have you considered doing this?
Yes, and it's actually not that much of a social challenge. So Alex Nastain, who's the main developer, is very willing to make some changes. In some cases, it makes sense to have these things, like for instance, applying term ordering to your literals after applying inference rules just makes a lot of sense for future steps. In other cases, some of the changes, especially of order of literals, happened more or less just because it didn't matter at first, and that's how it was implemented. So we've already changed that in some cases. In other cases, however, it's either a bit harder to change without just introducing more unnecessary work for the prover, and of course, with automated reasoning, you always want your systems to be quite fast. But yeah, in a lot of cases, it's definitely true that you can change the original implementation, and also has been done already. Yeah.
Or just get some extra information. So for example, when you do the permuting of the clauses and stuff, do you have to calculate the permutation yourself, or is that given in the proof?
So it's not by default given, and then when you're trying to do these verifications, it's always a bit of a trade-off between actually keeping track of stuff like that during the proof, because then you're carrying around more information, and sometimes you have to compute things during the proving process. Sometimes it's cheap and not that much stuff to save, and in these cases, that's what we do. In other cases, it may be quite easy to compute stuff afterwards, for just comparing, for instance, the literal to see if the sides were swapped and stuff like that, and then we do it afterwards. So it's a bit of a mix. It's always a trade-off, so you consider it every time.
Any other questions? Okay. And now we go for lunch.